Hi, and welcome to this fifth lesson on derivatives. In the first four lessons concerning derivatives, you have mostly been concerned with how to differentiate. You have learnt various tricks and theorems which help you to find derivatives of complicated functions in terms of derivatives of simpler functions. In this lesson today, we are going to use all this body of knowledge that we have acquired to apply derivatives in practical situations. You will find this a very interesting aspect of derivatives and of the calculus. But to do that, I want to refix your notions which I had discussed at the beginning of these lessons on derivatives. Remember, when I introduced the notion of the derivative, I told you that it is really a rate of change, and I also explained why it was. If you are now measuring the rate of change of distance against time, you would call this in some sense speed, or if it is motion in a straight line, this would also be velocity. But at the instant of time, remember, derivative has been coined as instantaneous rate of change. Let me fix this properly. I have this written down for you over here. Let us take a look at that. Suppose that an object is moving along a straight line with distance at time t given by st. This is with respect to some coordinate system. If st is differentiable, then s prime t is called the velocity of the object at time t. So, let me re-emphasize, when I had first introduced derivatives, I had told you that for this kind of a physical situation, s prime t has no other option but to be velocity at the instant of time t, and that is what we designate it as in this physical situation that I had discussed. Furthermore, in such a situation, I have something more to fix for you. If the velocity is itself differentiable, then the derivative of the velocity, that is s double prime t, is called the acceleration of the object. Remember, s double prime t is the second derivative of st, and by our notion of derivatives, s double prime t is the rate of change of s prime t. Since s prime t is velocity, rate of change of velocity would have to be acceleration, of course at the instant of time t. Well, having fixed that for you, I now wish to draw your attention to some very interesting applications of our notions of the derivative in physical situations. I am going to discuss some problems one by one. I have them written down here for you, and let us take a look at the first of these problems. Here it is. The position s in meters of a particle moving in a straight line is given by this equation: s at any instant of time t is t cube plus at square plus bt plus c, where t is the time in seconds, a, b, c are constants. If you are given that at time t equal to 1 second, the distance travelled is 7 meters, the velocity at that instant of time is 7 meters per second, the acceleration at that instant of time is 12 meters per second squared. Find the constants a, b, c. So, here you are given some data about velocity, acceleration and distance travelled, and we have to find the constants a, b, c. Well, let us apply our notion of velocity and acceleration to this equation for distance. Let me just put it down on paper for you. I am given that s is equal to t cube plus at square plus bt plus c. Now, what will be the velocity? The velocity would be ds by dt at the instant of time t. By our knowledge of derivatives, ds by dt would be thrice t square plus twice at plus b. What would be acceleration? It would be the second derivative of s, or the derivative of velocity, d2s by dt square. That is the derivative of this expression, that is going to be 6t plus twice a. We are required to find a, b, c, and we are told that at time t equal to 1, at time t equal to 1, s is equal to 7. Well, when I put t equal to 1, s is really, by this expression over here, 1 plus a plus b plus c. That is the first of our equations. Let me just put it down on this other sheet of paper. So, at t equal to 1, I find that 7 is equal to 1 plus a plus b plus c. Also at t equal to 1, I am told that the velocity is given by 7 meters per second. So, once again 7 would be equal to ds by dt at t equal to 1, but ds by dt is 3t squared plus twice at plus b. So, when I put t equal to 1, I get ds by dt as 3 plus twice a plus b. So, 7 is equal to 3 plus twice a plus b. I am also told that the acceleration at time t equal to 1 is 12. So, I find 12 would be equal to, from this expression, 6 into 1 plus 2a, 6 plus 2a. We are required to find ABC. We have 3 equations in 3 unknowns, and I am sure you will be able to solve these equations and find the values of A, B and C from here. So, we put our knowledge of derivatives over here to find these constants A, B, C, and that would give us completely the knowledge of the motion of this object or particle that we were discussing. So, remember that derivative at an instant of time for a moving particle in a straight line gives you instantaneous velocity, or velocity at that instant of time. But how does velocity really vary as we vary the expressions for velocity? What do I really mean? Expressions for distance, what do I really mean by that? Let me just put it down on paper for you, a quick discussion on this. See, suppose I have a particle moving on a straight line and its distance is given from some coordinate system fixed, its distance at instant of time t given by the expression x t. And suppose I had some other particle moving like this, x t squared, that is the distance from at time t from some fixed origin. Would the rate of change of distance against time for this and this be given as the square? In other words, would the derivative of this be the square of the derivative of that? And the answer is no. You have already seen such instances earlier. A simplest situation would be when your function x t would be equal to, say, t, then x t square would be equal to t square. The rate of change of this with respect to time would be 1, dx by dt would be equal to 1, no matter what time you took. Over here, by the chain rule, you would get twice x t into dx by dt. That would be the rate of change, the derivative of this expression with respect to time. Well, actually that is going to be equal to just twice t, and you can see that twice t is not the square of 1 for various values of t. So, it does not vary according to the algebraic relationship between the two. There is a totally different connection between derivatives and their powers or whatever other functions that you take of those functions. I now want to discuss another example with you. Here is the example that I have in mind. Let us take a look at that. For a car running on a straight road, the distance s is given by the expression s equal to t square minus twice t, where t is the time in hours and s is the distance in kilometers. When the odometer reads 15, what is the speedometer reading? In other words, when the car has traveled a distance of 15 kilometers, what is the velocity of the car? That is the problem for you. Well, we first need to find out, if the car has traveled 15 kilometers, how much time did it take to do that, or when it is at the distance 15, what is the instant of time? So, by the expression s equal to t square minus twice t, I get 15 is equal to t square minus twice t, or t square minus twice t minus 15 is equal to 0. That gives me t as equal to, solving for a quadratic, t is equal to 2 plus minus under root b square, that is just 4, plus 4 AC, 15 into 4, that is 60 upon 2. That turns out to be equal to 2 plus minus under root of 64 is going to be 8 divided by 2. That is going to be equal to 10 upon 2 and minus 6 upon 2. That is going to be 10 upon 2, and 2 minus 8 will be minus 6 divided by 2. We discount this straight away because our car is moving in a straight line. So, its distance is always being measured in positive as a positive quantity. So, at the point where the car has reached 15 kilometers, the instant of time is going to be equal to 5. Okay. Now, the question asked was, what is the speedometer reading when the car has reached 15 kilometers? Well, the car reaches 15 kilometers at the instant of time t equal to 5. Let us define the velocity of the car at instant of time t equal to 5. ds by dt, that is the velocity of the car at instant of time t, that is nothing but twice t minus 2. And at instant of time t equal to 5, that is just going to be equal to 2 into 5 minus 2, which is equal to 10 minus 2, which is 8. So, the speedometer reading in this instant is going to be 8 kilometers per hour. That is the rate at which the car was traveling when the car reached the distance 15 kilometers. See, that is a nice application of a derivative. Let us look at some more problems over here. Here is another problem. A ladder 13 feet long is leaning against a wall. If the base is being pulled away at the rate of half feet per second, how fast is the top of the ladder being lowered when the base is 5 feet from the wall? I think it is best if we draw a diagram to understand this problem. So, let us see if we can understand the problem in terms of a diagram. Here is the wall. Mind you, this is a vertical wall. Here is the ladder leaning against the wall. The ladder is being pulled in this direction. I'll call this the positive direction of the x axis. Let us fix the origin over here, and I am told this is 13 feet, this distance from here to here. This is the x coordinate, this is the y coordinate, and this part of the ladder is descending in this direction, whereas the base is moving in this direction when the ladder is being pulled. We know that the base is being pulled away at the rate of half feet per second. So, of course, x is a function of time, so is y, and how are they linked? By Pythagoras' theorem, at any instant of time t, x t square plus y t square is equal to 13 square. Also, I am told that dx by dt is equal to half, that is given to me, and I need to find dy by dt, the rate at which this is descending, dy by dt, that is what I need to find. Well, how do we do that? Let us just take a look at this expression and differentiate this with respect to t. When I do that, this is what I get. I am going to differentiate this with respect to t. So, I am going to get twice x t dx by dt plus twice y t dy by dt is equal to 0. And remember, I need to find dy by dt. So, let us just see what we can do with this expression that I wrote here. Dy by dt from here turns out to be equal to minus x t dx by dt divided by yt. Okay. Also, I know exactly what dx by dt is. So, this expression further becomes minus 1 by 2 xt by yt. Let us just go back to the statement of the problem. The statement was the following. The ladder is 13 feet long. It is being, the base is being pulled away at the rate of this. How fast is the top of the ladder being lowered when the base is 5 feet from the wall? So, remember the base is 5 feet from the wall. Therefore, this xt is going to be 5 feet. So, this is minus half 5 upon yt. Okay. Let us just simplify this a little bit more by the use of Pythagoras' theorem. This is equal to minus half 5 upon under root 13 square minus 5 square. And remember, this is nothing but dy by dt, and that is what you needed to find. I will leave the simplification of this for you, but you have the answer over here. In fact, it is just a question of rewriting this. The negative sign, by the way, denotes the fact that the ladder is descending towards the origin. We will discuss this later when we discuss increasing and decreasing functions. For the time being, just take it the way I have mentioned it to you. Let us look at another problem now. I have one more problem to discuss. This is also motion in a straight line. Let us take a look at that. Two stones are thrown up simultaneously with motion given by s equal to 19.6 t minus 4.9 t squared. This is the motion of the first stone. The motion of the second stone is given by this expression, s equal to 9.8 t minus 4.9 t square. What is the height of the second stone when the height of the first stone is maximum? Let us just think carefully. What is the height of the second stone when the height of the first stone is maximum? Well, this problem may appear a little difficult at the beginning, but if you think carefully, there is really nothing much to it, just a simple application of derivatives. What do I mean by that? Suppose this is the second stone. Suppose this is the first stone and this is moving up. When will it reach maximum height? At the point where it ceases to move up anymore and will have to descend again. In other words, its maximum height will be reached when its velocity is 0. So, let us first find out how or where its velocity is going to be 0. That means we need to do a derivative over here. Let us take a look at that. Here is the expression for the first stone. The expression for the first stone for distance is s equal to 19.6 t minus 4.9 t square. What is the velocity? ds by dt, that is going to be equal to 19.6 minus 2 into 4.9 t. That is just 19.6 minus 9.8 t. And remember, maximum height means velocity is 0, as I explained to you a while ago. And therefore, when is ds by dt equal to 0? When 9.8 t is equal to 19.6. In other words, when t is equal to 2. So, at the instant of time t equal to 2, the first stone is at maximum height. What was our problem? Our problem was to find the height of the second stone when the first stone had reached maximum height. So, the first stone reaches maximum height at t equal to 2, and therefore, the height of the second stone is to be found at t equal to 2. What is the height expression for the height of the second stone? This is the expression, s equal to 9.8 t minus 4.9 t square. If you put t equal to 2 over here, you will get s equal to 9.8 into 2 minus 4.9 into 4. This is into 4 and this is into 2, and that turns out to be 0. So, the height of the second stone is 0. In other words, the second stone reaches the ground when the first stone has reached maximum height. You found that out by a simple application of derivatives. One more application of derivatives in a slightly different context. Let us take a look at this problem also. I have it written down for you over here. A water trough with vertical cross section in the shape of an equilateral triangle with one vertex down. So, it is something like this. Let me first tell you what I have in mind. It is something like this. The equilateral triangle is in this form. This vertex is down, and this is just a cross section, a vertical cross section of the trough, and this is the other part of the equilateral triangle, which I could sort of explain to you with a pen over here like this. So, that is the vertical cross section of the trough, water trough. Okay. Let us read the problem again. A water trough with vertical cross section in the shape of an equilateral triangle with one vertex down is being filled at the rate of 4 feet cube per minute. Given the trough is 12 feet long, how fast is the water level rising when the water reaches a depth of 1.5 feet? So, we are told that this trough is filled at the rate of 4 feet cube per minute. So, the volume of the water increases at this rate. Given that the trough is 12 feet long, how fast is the water level rising when the water reaches a depth of 1.5 feet? We need to just find how fast the water level rises. Well, I have a diagram over here for you that will probably make things a little clearer. Let us look at this diagram. Here is a more or less crude sketch of the water trough. This is the vertical cross section of the equilateral triangle. Here is water being poured into the trough, which is 12 feet long. Now, see the vertical cross section of water at height xt. So, if I were to take a vertical cross section and this was the height of the water, so this height is xt. Okay. Then the vertical cross section has area xt square by root 3. So, the volume is 12 times xt square by root 3. This is just simple geometry. You know how to find the area of an equilateral triangle, and from there you get the volume for this trough, which is 12 feet long. That is 12 times xt square by root 3. You are also told that the rate of change of volume is 4. So, V prime t is equal to 12 by root 3 twice x t into x prime t. But that is given to be equal to 4. Now, how fast is the water level rising when the water reaches a depth of 1.5 feet? So, you are told that when you are told to find out x prime t, the rate at which the level is rising, the rate at which the level is rising when the water reaches a depth of 1.5 feet. So, when x t is equal to 1.5 feet, so that is going to be equal to 12 by root 3 2 into 1.5, that is 3 upon 2 into x prime t. You can surely solve this equation and find out that if t naught, for instance, was the instant of time when x t naught was 3 by 2, then x prime t naught can be easily evaluated from here. Just take this to the left hand side by inverting it, and you will find x prime t naught, and that gives you the rate at which the water level is rising when the water has reached a depth of 1.5 feet. Well, I have discussed with you some applications of derivatives. There are lots and lots of applications of derivatives that you could discuss with me, but we need to move on to some other topics over here which are also applications of derivatives. I need to introduce some other notions over here but I urge you to try as many problems as you can on these rates of change, discussing velocity and other problems that I have discussed so far. The more you practice, the more you shall learn. What I have in mind now is to discuss certain properties of functions and to study their properties with the help of derivatives. Remember, when we were discussing functions in the beginning, there were times when we found that if I took two different values of the function, say two different values in the domain of the function, say x1 and x2, and whenever I found x1 was less than x2, I found fx1 was less than fx2, where the function was f. Let me put this down on paper for you. So I have a function from some domain, which in most cases for us is always an open interval, into the set of real numbers. There were times when we came across a function f like this, such that fx1 was less than or equal to fx2 whenever x1 was less than x2. Such a function is called an increasing function. There are lots of examples of increasing functions, and increasing functions occur all the time in nature. When you study motion and other things, you will find that increasing functions occur all the time. You could similarly understand what I mean when I say you have a decreasing function. What would that mean? Well, whenever x1 is less than equal to x2 in the domain of the function, then fx1 is greater than equal to fx2. In other words, as we take increasing values in the domain, the range has decreasing values. Such a function is called a decreasing function. It's best to look at examples to understand both kinds of functions. So let's first look at an example of an increasing function. Let us take I, this open interval, to be the whole real line. Let us take the function f of x equal to x. You can see very clearly that this is an increasing function. Let us take f of x equal to x square. What happens now? Well, you can check for yourself that if I take the domain to be this open interval 0 infinity, then this is going to be an increasing function. This is simple algebraic manipulation. I also want you to try this as homework, that when I look at the domain minus infinity to 0, the open interval minus infinity to 0, in that case this is going to be a decreasing function. So there are examples like this which are so simple to understand, which give you an idea of what an increasing function is and what a decreasing function is. We are going to study increasing and decreasing functions with the help of the derivative. I also want to show you some other properties in the next lesson concerning the derivative and properties of functions. Thank you.